First, I have two announcements before starting. So first announcement that Mathieu, so the project is going to start, and Mathieu has sent a message. He's going to have a lab session tomorrow. You saw the mail, but it will be held by Teams. And the reason is that Mathieu has been to the hospital and he's doing a radio education, but he can still make startup Teams. So the lab session will be on Teams, okay? But you can send him mail and anything, no problems. It's just that he can't move around so much. So that's the first announcement. November 23 on Teams. Okay, so you have the link for that on the Moodle. Second announcement, that there will be a seminar on November 24, given by Neil Davies, who's going to be visiting us. He's visiting this department, and this one is starting at 1 o'clock till 2 o'clock. If you were smart, you have asked for sandwiches. So those who have pre-asked for sandwiches will be able to get sandwiches before the seminar in the cafeteria of the department, which is Réaumur, second floor. Unfortunately, you can't eat the sandwiches in the auditorium. So we're holding it in the bar 91. And the reason is that there's going to be more people than usual. So it's people from the department, but also master students. But the sandwiches will be in the cafeteria before. Okay? So if you asked for sandwiches. If you did not ask for sandwiches, then there might be a few sandwiches left, but there's no guarantee. Okay? This seminar I consider to be part of the course. Neil Davies will give a much more intuitive explanation in a general kind of seminar. He'll give a lot of his experience, and my lectures are a little bit more theoretical. I'm giving you more the foundation. But if you listen to the lectures first, you will get a lot more out of the seminar. Because when Neil Davies explains something, if you understand what's really going on, if you understand something about the concepts, then you will get a lot more out of it. Okay? So that's recommended. But unfortunately, there won't be videos of the seminars available before then. They will be available by the end of the year, the videos here. And I will also try to record the seminar so that the people, you can look at it afterward too. Okay? So this one is from 13 to 1400. Okay? So that's the two announcements. Today I want to talk a little bit more, give some more theory and more examples of using ΔQSD. First, a few seconds of respect for the Ukrainians who are fighting for their freedom and for our freedom in Europe. I made an update of the slides. I will put the new slides on the Moodle, probably tomorrow. So here's a new table of contents. The ΔQSD, it's actually two parts. Oh, why is it flickering? I don't know why it's flickering. Sorry about that. Oh, it's flickering. Oh well, hopefully you won't get too many headaches. There's two parts, two kinds of systems. The first is systems that are compositional, so you put the pieces together and there's no dependencies. Every piece acts independent. That's the default. And we saw some of that last week, and I'll finish that today. And then the next step is adding dependencies, and that's really when you can predict what happens when you have high load. For example, congestion, when you have multiple message streams coming into the same component, or two components sharing the same CPU, if there is an overload, then you will see that in both components. Also, humans, iterative queries, when you have the variable load depending on recursive kind of operations. And I'll say a little bit about handling risks and how to design systems that can handle very high load. Okay, so that's the thing that most, even industry people don't really know, and that's the thing that P and Sol has worked on for 30 years. And I will give some of the principles, but I won't be able to say too much, but I will give the main principles of this. Okay. Okay, so let me refresh first your memory. So first, a refresher. The main concept is that delay is not a number. It's a distribution, a cumulative distribution function. So this function combines delay and failure and jitter, because there's variation, okay? So that's the delta Q. And the next thing is the outcome diagram. Let me make a small extra comment on one of the case studies. Last week we saw this case study where you had a whole system here made by some very large and very well-known mobile telephony company that everybody knows. Okay, but that doesn't mean that they're making perfect systems. The system had big problems. Then there's all these delta Qs between all the different parts, but I didn't really explain. So I'm going to explain a little bit better. If you have the system running here in a delay, each time you have each of these little circles is a packet delay. Measuring the delta Q is basically taking the vertical section here and graphing all these delays here, and this gives you this cumulative, They all go up to some, they start here, they go up to some point, and then it is less, so you have something like this, So the whole trick is, you want to measure the delta Q as the system is evolving, okay? You want to measure instantaneous delta Q, but that's not really possible because you have to actually get a whole lot of packets here to get a reasonable approximation of the delta Q. So you make some kind of approximation where you take some kind of a slice, maybe like 1 second or so. So you have the delta Q as a function of time. That's actually very interesting, because delta Q is also a function of time, the delay here. But this delay is changing as the system evolves, okay? And the point is, so I added some explanation. The point is that the delta Q is not stationary. That means the function delta Q is actually changing as the system is running. And sometimes it does really weird, it goes really weird. So here, the delta Q has some really weird behavior, okay, which we will explain today. And here is it kind of expanded at 595 seconds. You see this behavior. Notice it goes up very quickly and it goes down slowly, okay? That's actually very important because it shows that there's a buffer problem here. When this is going up, each Q in the system, so each component, if I have a component here, and packets are coming in, and they are being queued up, and then they're treated, okay? So there's a buffer inside here. Now, if the packets arrive too quickly, the buffer will fill up. That's reasonable. That's supposed to be quite good because then eventually the packets will be treated and the buffer will go smaller again. But if the load is really too big, if the packets arrive way too quickly, the buffer will be filled up, of course, but the queue has a certain performance. It can handle certain number of packets per second. And so this huge queue is being slowly decreased as the queue is working on the things. Okay, so it's emptying slowly. Get into trouble very quickly. You fill the buffer. Get out of trouble slowly. The buffer can only be emptied slowly. Okay, so I added some explanation there. Okay, so this we saw last week. Cardano-Shelley, I'm going to explain it today. This is the blockchain. Okay, so the quality attenuation, so that's the basic concept. It's the delay, but it's three things. It's a number, but actually many numbers. But it's also the chance of failure, because this will not go up to 100%. And there's also this variability, that there's this probability, and this is the jitter, the fact that the delays are different for packets, different packets. And it's a probability distribution because we assume that the packets are independent of each other, okay? So the basic idea is by default, it's independent. And then we add the dependencies later, okay? So we saw that last time, and you can compare them. Combining them is doing convolution, okay? This is a very important operation where you combine two delta Q functions to get another one. So it's in this integral. And it's used in many areas of engineering, physics, electronics. It's a very important operation. So it's used here to combine when you connect two components. Okay, so we saw some of this. I made the uniform distributions. So the idea is you want to, let's say we had this design here. We know the total delta Q, and we know B is delay, and we have to buy a component here. Okay, so we're designing. We have to figure out what goes here. But we know what the total delay has to be, and we know that we have some constraint. Maybe this is a network with some performance constraint. So we have to figure out what can we put there in the A. And there's some constraints on the delta QA. And you can actually do it by hand if you have a simple delta Q. So in general, it's very complex because the delta Q is very complicated and it's a deconvolution. But if you assume the delta Qs are uniform, you can actually do it by hand. And I made it more precise computation. So for example, little a is the delay of A, C and B are the delay of C and B. Now the delay of A plus the delay of B has to be less than the delay of C. That's logical, right? But they're distributions, they're not numbers. And that means it's actually a little bit worse. That means because they're distributions, you have this little extra thing. Because they're not instantaneous constants, the delay of A has to be maximum C minus B minus a little extra number. Okay? So this little extra number is because it's not constant, because it's a distribution. If you do the deconvolution, you get it precisely. Here I'm assuming it's uniform. Okay? And there's a more complicated computation. I'm not going to show the whole thing. You can actually determine if you know B and C, maybe it's impossible to find an A, okay? Maybe the B is already so bad that there's no way to put an A in there that can make this C, okay? So of course it's nice to know that before building and paying lots of money, and you can compute that. And here I computed for the uniform distribution. And if B and C satisfy this condition, then it's impossible. Then you cannot do it. There's actually two possibilities. Of course, if the spread of C is less than the spread of B, that's clear. If B is already very bad. Or there's another condition, and this one comes from the fact that it's a distribution and not constant. Okay? So I'm not going to go in detail. It's just to show you that while you're designing, you can actually figure out whether it's possible or not. So if it's impossible, it's called infeasible. Huh? Okay, and now let me go to outcome diagrams. Let me just give you a couple of examples to refresh your memory. Outcomes is what you see. It's observational. I'm looking at the system from outside, okay, and I see things happening. I see database query, and I see a response, and there's a delay between the two. And that's an outcome. So an outcome is a pair of two events. So user click, I click on my keyboard, and a query is created in my browser. There's a program that runs. That's an outcome, okay? And then the query is sent on the network. And that is also an outcome between creating and sending. And it actually arrives at the server. Between entering the network and entering the server, there's a delay. So that's another outcome. And the server responds, so there's a delay. That's the computation of the server. And then the network back the other way is another delay. Here's another delay. Eventually it's displayed and the user sees it. So this human being here, okay? And the total delay is just the convolution, so the sum of all of these delays. Okay? So that's a way of understanding how systems work. Now, let me show you a couple other examples. Here's a nice example, a cache memory, okay? A cache memory, so you have a cache sitting in front of the main memory, and this is used, of course, everywhere. They even have multiple levels of these, but I'm only showing one level, cache here. The processor does memory read. If it's in the cache, the result comes back very quickly. If it's not in the cache, it has to go to main memory, and it's slower. And you could model that also as an outcome diagram. So I'm doing the read. This is the read event. And here I have something called probabilistic choice. So the cache, there's some chance that it's in the cache, your memory word, and usually it's high. It's called hit ratio. Say 95% chance it's in the cache, for example, and then it does a hit before you return. But there's a 5% chance it's not in the cache, so there's a miss, and then it actually has to do a main memory read. So it has these two things. And combining all these, you can compute the delta Q. You see how nice it is, huh? Using the delta Q's of these pieces, you can find the total delta Q of the whole memory. And this is the equation. So the miss and the main is a convolution, but the probabilistic choice is just a weighted sum. So that's much easier. Where H and M is hit and miss. And then I showed you how you can do that. This is when there's that they're constant. The step function means that the main memory, for example, it's always 4 cycles. Okay. Then I explained a little bit the semantics. So the semantics is basically computing on these delta Qs, and there's 4 operators. The sequential, when one is connected to the other, probabilistic choice, one or the other, and then 2, which are more like synchronization, last to finish. That means I wait until both of these guys finish, so it's this and that, and you can compute it, it's multiplication. And the other one is first to finish, where I'm waiting where one of them finishes, the first one. And this is another formula, okay? And I give you an example. So this is an example of a timeout. I'm sending something into the cloud, and I get a response. But maybe it's slow, and there's a timeout. At the same time that we do send, I initialize this timer, and the timer gives me this timeout, and then I merge the two, which basically I'm taking the first one. So the outcome diagram is this diagram, where I have first to finish. I have the cloud outcome and the timer outcome, and you can see the two time delta Qs. So the cloud was like this, and maybe it's really slow. The timeout is a fixed time, and then it's 100%. And if you do this computation, you get this. So basically, up until the threshold, you get the response. After that, you have 100% response, but it's the timeout and not the actual response. So you're guaranteed that there's going to be a response always after this time. But it might be just that you get a timeout, okay? So this is a single number, a single thing, this distribution that you can compute with. Okay, so that's another example. Now, I want to go more into some nuts and bolts stuff. I want to show you some typical delta Qs in real life. Okay, you have to, as engineers, you have to kind of know what's going on in the real systems. And so I'll talk about Gaussian and the uniform distributions, a little bit of theory. And then there's two kinds of things, parts. You have components, like databases or browsers. And you have networks that communicate. And they have different delta Qs. So we'll just take a look at what are the delta Qs for those two things. Okay. And so the component delta Q will be computed using queuing theory, and the network will be actually measured. So the people at PNSOL, they actually measured it, and we'll see what it is. Okay. So it's very good for an engineer to know some delta Qs. For a software tool, it doesn't really matter, because the tool can do any kind of complicated delta Q. But you need to know to do back the envelope. It's really important to have some intuition, and I'm going to show you two here, Gaussian and uniform. And they're basically doing completely different things. A Gaussian approximates when you have a whole bunch of things, aggregates. And a uniform is like a single component. Okay? And this is something that you've probably seen. If you take a whole bunch of independent random numbers and you add them together, it becomes Gaussian. You've seen that, right? You remember that? Central limit theorem. In French, théorème de limite centrale. No, it says something to you? It's a very practical thing. It means you add a bunch of random numbers together and it always turns into a Gaussian. Okay, which is very interesting, actually. Gaussian is very special. Okay, so the Gaussian is a good approximation for bunches, for aggregates. Okay, but not for single things. The Gaussian is very bad. If I have a single component or single network, then the Gaussian is not actually good. And one of the bad things is the Gaussian has this infinite tail. It goes on for a long time here. And real systems don't have that. They have some limit there, okay? So Gaussian doesn't work for single parts, like components or networks. And much better is uniform for back the envelope, which is 0 up to some little point A, then it goes up like a straight line, and then it's 100%, okay? Uniform distribution. It's a good approximation for single parts. And you can do computation, so I'll just very quickly, Gaussians are so beautifully nice. If you do the convolution of two Gaussians, this complicated integral, well, it's also Gaussian. You can do it as an exercise. And the mean is the sum of the two means, and the square of the variance is the sum of the two squares. So that's really nice, right? The sum of two Gaussians is a Gaussian, okay, when you do convolution. Okay, why is this square of the variance equal the sum of the two squares? Why isn't the variance equal to the sum of the two variances? That's actually really interesting. It's because you have two independent random variables, and when you add them up, they can reinforce or they can cancel each other. The one might be higher than the mean, the other one might be less. So when you add them up, they kind of cancel each other out because they're independent. That's why the standard deviation is not the sum. And that's why the square is the sum of the squares. And it means if you add a lot of them together, the standard deviation does not spread out so fast. It increases more slowly than just adding. And it's basically because they're independent. Okay? And this is a convolution. Okay? For uniform, you can also do convolution, but this one is an approximation. If I take these two uniform guys and I do convolution, the red curve is like the exact thing. So this is like polynomial. It's like a parabola, going up and then going back. But I want to do back of the envelope, so I approximate it. Okay, so this black line is like an approximate uniform. And you can see the minimum is not A plus B, it's a little bit more. Okay, and the maximum is not big A plus big B, it's a little bit less. And this is only a couple of % difference. Huh? So this is actually pretty good approximation. And the spread is wider than the sum of the two spreads. Okay, it's going to be, it's actually not the sum, it's the maximum of the two. The one that has the widest, is kind of dominating, but the other one will have its effect and will increase a little bit the spread. So that's how uniforms convolve, okay? So this is very nice for back of the envelope, okay? Okay, so that's a little bit of theory. Now, what happens with real components and real networks? The delta Qs are really important things. So what happens if I just take some random piece of hardware or whatever? The delta Q, you can actually, a lot of the time, you can model it using queuing theory. Has anyone here seen queuing theory? Have you seen? You've seen queuing theory? Anybody else has seen queuing theory? Ah, well, the guy who has seen queuing theory, this will be extremely familiar for you. The other guys, it will be a new thing, but a very interesting thing, I hope, okay, and still intuitive, okay? So here is a component, random component, piece of hardware, piece of software with input and output. What is the delay? Okay, what is the delta Q? Well, we'll model it as a Q, and a Q is a very specific mathematical thing. A Q is a box where you have things coming in, things coming out, and inside you have a buffer and a server, okay? And you have 4 parameters. A queue has 4 parameters. How fast are messages going in? That's called the offered load. So the load is how much you're loading the system, how many messages are going in. We actually normalize it. The queue has a kind of built-in speed, which is the service rate. Maybe it takes 1 millisecond to treat every packet. And so the arrival rate, we normalize it. So the offered load is equal to 1, then it's exactly what the queue can handle, what it can handle, okay? If it's less than 1, then it's less. And maybe it's only half or 1/10. And then there's also a buffer inside here. I mean, if messages come in very fast, they're usually not thrown away. They're stored in a buffer, and the buffer has a size. And whenever you buy a piece of hardware or a network card, it will have a buffer in there. So those are the 2 inputs, the things you can control. The buffer size, you control it when you build the queue. The load is actually something that's happening when it's running. And then you have 2 results. You have failure rate and delay. So that's like outputs. And notice these 2 are actually summarizing the delta Q. Really, you have a delta Q here. But let me just talk about failure rate and delay. So you have an expected average delay between input and output. You also have failure rate. If the buffer overflows, the messages are thrown away and they're dropped and it's failure, okay? So the 4 parameters are related. These 2 are like inputs and these 2 are outputs. That's the intuition. Now in queuing theory is a discipline of operations research where you study the mathematical properties of different kinds of queues, okay? And there's many different kinds of queues. The queue I'm going to talk about here is called an MM1K queue. Now, you can have many different kinds of queues, but this one is an MM1K. Why is it called that way? Because you have messages coming in here, you have a buffer, and then you have a server, okay? The server can handle 1 message at a time, and the buffer has size k minus 1, so the whole thing is size k, okay? And there's an arrival rate, lambda, which is messages per second, and the service rate is how many are treated per second. So the offered load is actually lambda divided by mu. Okay. What does MM1K mean? M, the first M is what is the distribution of the arriving messages? Are they Bernoulli messages, exponential, whatever? Are they following a gamma distribution, whatever distribution they follow? So M means exponential. That's weird, right? Why not E? M means exponential because the M actually stands for memory-less. An exponential distribution of input, it means the packets have no memory. When one packet comes in, it does not affect when the next one comes in. It doesn't actually remember. Each packet is independent. So that's an exponential distribution, and that's N. Okay? And the server here also needs time. But it's not constant time. Again, the time varies. And it varies kind of randomly. Again, sometimes it's faster, sometimes it's slower. Again, it's exponential. So MM means both arrival and server are memoryless. So that's very common. Huh? The one means you only have one message at a time. Sometimes you have queues with multiple servers. Huh? They can handle 4 or 5 messages at a time. No, this one is only one. And the K is the size of the buffer. Okay? It's the total number of messages that can be stored inside. Okay? So the two knobs, the two things we control here are the load, A, and the buffer size. The buffer size is when we manufacture the queue. Huh? We can buy queues with big buffers or small buffers, but the load actually is something that changes during execution. Huh? And the result is that every message that comes in has a delay and a failure rate. If the buffer is full and a new message comes in, it's dropped. And then that's considered failure. So having a full buffer is not good, okay? But there's also a delay. If I have 10 things in the buffer here, and the 11th thing comes in, that 11th thing has to wait until all those 10 things are handled. That means there's going to be a long delay for that 11th guy. And each of these 4 before guys will have exponential distribution. So there'll be a sum of 10 random variables exponentially distributed with a rate mu, okay? So the more that's in the buffer, the longer the delay. That's not good either, okay? So the failure rate and delay is function of A and Q. Many, many, many components can be modeled like this, okay? So MM1K is actually a very generic and nice way of modeling components. And it gives us a lot of intuition, and I'm going to give you some of that intuition. The most important parameter of this thing is the load. How many things are coming in? The offered load, that's kind of intuitive. Huh? If I put in too much, I will stress the queue and things will go bad. But let's see how bad. Okay? Now, if A is less than 1, I'm good, right? Because the queue has enough power to service all the messages, because the service time is short enough compared to the load. Okay, the load is low enough so that it can service everything. And if A is greater than 1, the component is overloaded. Huh? I won't be able to do everything. So I'll have to actually throw away, because I can only do a part of them. Okay? But it's actually worse than that. It's the threshold in real life is not actually 1. It's less than that. Even if you model this mathematically, you can see that even for numbers less than 1, it gets very bad. Why is that? Because it's exponential distribution. That means it's a random number for each packet coming in. And sometimes it's very big. Okay? Now if I have 10 random numbers, some of them are going to be very big. Okay? That means even if the load is small, it can be very bad. And kind of more realistic, it's 0.8 is kind of realistic. maybe 0.7, depends on what you want. So if you have very low load, the failure will be 0. That's good, huh? You don't throw anything away. And the delay will be very small. So the best delay is 1, huh? Because you have to do the server, and that's 1. So if you have very low load, it's going to happen very well. Underloaded component behaves very well. That's nice, right? Huh? The problem is not that. The problem is here. When A gets close to 1, even like 0.8, it gets very bad, okay? And when A is bigger than 1, it's really bad. So the failure rate is A minus 1 over A. So let's say A is equal to 10. I'm putting 10 times as much load into that queue as it can handle. Well, 90% of the packets are going to be thrown out. Huh? Okay, that's reasonable. Huh? That's what's going to happen. And the delay will also increase a lot. Why? Because the buffer will be always full. And when the buffer is full, when a new guy comes in, it has to wait until all of the preceding ones are done before being handled by the server. So it has a very high delay. The delay increases very quickly when A approaches 1. So 1 or 0.8, or actually in between 0.5 and 1, is kind of a phase transition, a switchover. If it's less than 0.5, we're golden, we're great. But if it's bigger, we're bad, okay? The system quickly gets very bad, okay? And even a temporary overload causes a big, long-lasting degradation. So let's say that the load is fluctuating. It's fluctuating. And like sometimes it has a peak, very high peak, short peak. Well, what happens? During this peak, the buffer fills up and it's full. 1,000, maybe it's like 1,000 packets. Well, all of the packets after that will suffer because the buffer has to slowly go empty again. Even temporary overload causes a big, long-lasting degradation. This is exactly what was happening in the small cells. There was a peak that caused everything to break. This is important. If you forget everything else about ΔQSD, remember this. Never overload a component, not even temporarily. Unless, of course, you've designed for it, okay? Which the guys at this big unnamed company did not do. Of course, you can design for that, but that's not easy. So by default, never overload a component, not even temporarily. So we can see that in terms of delta Q. Here are 3 delta Qs. Here's for very low load. Here's for the load equal to 1. It's already bad. And here it's greater than 1. So this one, A less than 1, is very good. So if you do the computation, there's a delay here. And this delay is A times S over 1 minus A, where S is the service time, okay? And as A is very small, this will go to 0. The S is the constant. So this is my approximation of an exponential. So I'm approximating it as uniform. And then there's almost no failures. The buffer will never be full. So it will go up to 100%. This is good. Very good. Now if A equal to 1, it's already very bad. The delay, it's K over 2 times S. K is the buffer size. Here the buffer is size 10. So the delay is 5 times S. But if the buffer is 1,000, it will be 500 times S. Okay? And there's already some failures. 1 over K plus 1, 9%. Not so good. But if A is big, the delay will get up to K times S maximum. So it'll be 10S, which is a lot. And the failure will get really, really high. Eventually, almost all the packets will be thrown out. Okay? So the buffer is really a curious beast. So let's look at the buffer size. Okay? The number of messages that can be stored in the component. Manufacturers, they love to brag, boast about the buffer size. my network interface card has 1 megabyte of buffer, woohoo. They brag about that. And bigger is better, right? Nope, that's not good. In low load, yeah. If low load, the bigger buffer will indeed decrease failure. It slightly increases delay, but that's good because we decrease the failure. Okay? So big buffers are good, but only at low load. And they're not that good, okay? If the load is very low, then you don't need a very big buffer to have very low failure rates, okay? Now at high load, so already the failure rate and the delay are high, but a bigger buffer will make the delay much bigger. So it will be k over 2, or even up to k times the server time. So the NIC, a NIC, which is a network interface card, which is something you buy and it costs a lot of money. If the buffer is 1,000, if you can store 1,000 packets, those are very bad actually. They like to boast about that, but you must never overload one of these. So the rule is, if you want good behavior, first of all, don't ever overload, not even temporarily, and 2, don't make very big buffers. Try to keep the buffer size small. Okay. So that's the queue. That's the model of a component. Okay. The MM1K queue. It's all a mathematical computation, and you can see there's many books. If you type this into Google, you will find huge amount of documentation on this. So I just give you the summary. Okay. And here's a simple example of the queue model. I want to do load balancing. That's neat, huh? I have things coming in a lot, and I make 2 servers so that they share the load. So there's a load A coming in here. I split it, P times A, Q times A. P and Q are fractions, okay? And I have 2 servers. And these are these queues, huh? So P times A is the load for server 1, Q times A is the load for server 2. Okay, and here's the outcome diagram. It's using probabilistic choice. That means each packet is either going up or down. It's one or the other. It's a choice. Okay, and the total delta Q is just a weighted sum. And if P and Q are both equal to 1/2, for example, then the 2 servers will get half of the incoming load. And if you want P times A to stay less than 0.8 for good behavior, then actually the total load can go even higher. It can go 1.6, so we're good. So this is a very easy model of load balancing, and you can make this much more complicated. You can find low and high priority packets. You can have different kinds of servers. You can have servers geographically far away, whatever. This is just the simplest. But it lets you compute the load balancing. Okay, so that's enough for components. Now let's look at networks. A network. Okay, so the network also has a delay. So here's a network, which is this cloudy thing here. Packet comes in here and comes out in Japan, for example, and there's a network in between. And this has some delay and also some failure probably. Now, how do we determine that? So that's not a mathematical computation, that's experiments. This has been determined by P and Sol by doing lots of experiments. And the experiments show that this delta Q actually has 3 pieces, which I will explain. G, S, and V, and the total delta Q is just the sum of those 3, okay? But let me explain them. So let me show you the kind of experiments that we do. So here we have a network. Each of these little pluses is a packet going through. So the network is running, okay, elapsed time, and each of these crosses is a packet that made it through, and this is the delay. Observed delay between the measurement points in seconds. So from 0.15, 0.15 to 0.045 for this network, between A and B. So this is what you measure when you send packets. But how do you understand that? You have to try to decompose it. Well, first of all, you can sort it by packet size. These packets, each of these packets is going to have different size. And sometime, maybe the longer packets are going to take more time, and that's exactly what happens. Okay, so here is the packet size in octets, and here is the delay. So this is the same diagram as before, except now I sort it, not in terms of elapsed time, but in packet size. So you have this funny, fuzzy line going up. And now we can study that. You can see the bigger the packets get, the slower it gets. Okay, so that's logical, huh? Okay. So let's analyze this thing. Assume we have a hypothetical zero-length packet. We make a line going, crossing here, the y-axis. This is going to be the transfer time for a hypothetical zero-length packet. Okay? And this line, this green line, is like a lower bound. This is a network where all buffers are empty. There's no contention. Each packet is like going by itself. It's not slowed down by anybody else. All the others, they have to wait because of buffers and stuff. Buffers mean slow down per packet. Okay, so the first parameter is this one, is the minimum time. And this one is called G for geographic or given delay. This is the structural minimum delay, so it's speed of light plus the overhead of the routers, the hardware speed. This is as fast as it can go. Okay. The next one is that the delay, it goes up when the packets get bigger. This is called serialization or size-related delay. It's because big packets, they spread out over the network. They have to be turned into sequences, okay, into a bit stream, and on the other side they have to be collapsed again to a packet, and that slows them down, okay, and this is how it slows them down. So that's S. The S is a function of packet size, whereas G is a constant. And then the third one is this funny, fuzzy fluctuation. It's not a constant. This is depending on many things. It could be contention. If I have two packets going into a router, even if it's low load, the packet coming in, the other one might still be in the buffer. It will slow down the one slightly. There's a little bit of contention, but it can also be because of noise. That electrical noise and stuff can also cause delays. Okay, so that's kind of a random thing. It's either based on contention or kind of random effects. So that makes three effects. So this is the experimental. You have the geography, fixed delay, the size-related delay, and then the variable delay. So those are the three basic elements. Okay. So the overall delay, again, it kind of looks, I'm going to approximate it like a uniform. You have the geographic, which is a constant for each network. Size is a function of the packet size. And this variable one is kind of a random thing that is fluctuating. Combining all three of them gives something like this. Notice it does not go up to 1 because each of these, I didn't say, but there's also a loss percentage. Some packets are lost, okay? So that basically reduces the maximum to be a little bit less than 1. So this is the measured empirical delta Q of a network, okay? So now we know the delta Q of a network and the delta Q of a typical component. And now we can start doing more design things. So now I want to do more design and also designing for overflow. For overload. Okay, so I'm going to now present to you the second case study, the block diffusion. So this is going to blockchain territory. And let me just make a quick summary of what's going on. Okay, I'm going to tell you this algorithm exists. It's implemented. It's part of an existing blockchain called the Cardano blockchain, which has supporting many things, including a cryptocurrency, which is called ADA. I don't know if you have bought any ADA coins, but if you have ADA coins, this is the software that's running them. So I hope that what I will say will increase your confidence that it's being well managed and so on and so on. It's actually not bad. It's actually a reasonably good design. So what is it? Let me just give a simple explanation. What is a blockchain? Okay, blockchain, of course, is highly mediatized. It's just a distributed ledger. So what is a ledger? A ledger is a book where all financial transactions are written in. So in the bank, in an accountant, transaction between A and B, transaction between C and D, they're all written in a book. Of course, this book is very important, very precious, must not be counterfeited and so on or destroyed. Huh? So a ledger is a book in which financial transactions are recorded. A blockchain is a software implementation of that, which is a distributed system. So this ledger is basically copied over many nodes. And how do you guarantee that the ledger is correct? Well, it's actually a chain. That means I have a first block, the next block points to the previous one, and so on. So you have this chain. And each time I do a new transaction, it adds a block to this chain. Okay? And each block is in some sense a witness that all the previous blocks are correct. So they all are managed using, they're all cryptographically protected, okay, with private keys. And the chain, there's only one correct chain, okay, one sequence, which is the global sequence that everybody agrees on, okay? And even if people try to attack, try to fake it, the algorithm is such that it can defend itself. There will be one global agreed upon chain. And when I do a transaction, the algorithm will add a new block to this chain, okay? Now how is that done? I'm not going to explain the whole thing, but there is a consensus algorithm because of maybe many nodes want to add transactions. So they run a consensus algorithm and say this one is added first. This is a decentralized, cryptographically secure consensus. So it's even stronger than the ones you saw in the course. It's a very special kind of consensus algorithm because it's a cryptographically secure one. And this algorithm then agrees, we run this algorithm, and it agrees that we can, this block will be added, okay? The algorithm is called, for Cardano, it's called Ouroboros-Prowse. So they invented this algorithm. There's many variations. All the cryptocurrencies and blockchains have their own ways of doing it. In Cardano, it does something called proof of stake, unlike Bitcoin, which is proof of work. So in principle, Cardano is more scalable than Bitcoin. So after you run the consensus algorithm, you have to select a node that produces a new block, okay? So you have selected a node that will actually produce the new block. It's chosen randomly. And of course it needs a copy of the preceding block, because it's a chain. The most recent one, preceding, must be copied to all potentially block-producing nodes. So many nodes are potentially block-producing, and each transaction will be produced by one of them. Okay? And so the chain, the end of the chain, has to be copied to all nodes which might be block-producing. And that has to be done in real time. That part of the algorithm is called block diffusion. It's also very important. It has to be fast. Okay? So that's the algorithm I'm going to explain now. So I'm not going to explain the consensus algorithm, but I will explain the block diffusion algorithm to some level of detail. And this algorithm, it took the company that does this is called IOG. They used to be called IOHK. It took them several iterations in order to come up with actually a really good block diffusion algorithm. The previous one, before Shelley, the one I'm going to display, was not so fast, okay? And so they were kind of worried. And this one was designed using ΔQSD with delta Q measurements everywhere to guarantee that it's fast. And so this one is actually quite good performance algorithm, okay? Okay, so that's all the introduction. I hope now you're all sitting on your edge of your chair. You want to know how this thing works, okay? So now we make a break. So let me continue the example of a block diffusion, the Shelley block diffusion algorithm, which is used in the Cardano blockchain. And I'm going to explain in two parts. Because block diffusion, you have to diffuse or broadcast, in a sense, the most recent block to all potentially block producing nodes. And it has to be fast. So this is in real time. So there's some real-time constraints, okay, to make it work. And so there's two parts. The first part is I have a network. So here is a node graph. So let's say this is the node graph of the Cardano blockchain. All these nodes are part of the Cardano blockchain system. And I pick two nodes randomly, A and Z, because of course they are random. Let's say A has the previous most recent block, and it has to be sent to all of them, so it has to be sent to some random node Z. So the first thing to do is to find out what is the delta Q between A and Z, okay? And once you do that, you have to design an algorithm. And we'll explain that. So the algorithm, how does it work? Well, there are a number of techniques you can use. For example, if a node has neighbors, you can measure which is the fastest neighbor. Or if you have a packet to send, you can divide the packet up into a header and to a body. And the header is very small, okay? And send first the header, and then send the body only if you need to send the body. So there are different techniques there to make it fast. And so we're going to do it in two steps. So the first step is to determine delta Q, okay? And then after that, we're going to define the algorithm, okay? So I'm going to first show you how to determine delta Q, and then we will do the algorithm. Now I will show you part of the design. Now we're designing an algorithm, a complex distributed algorithm. Remember in the previous lecture I showed this design tree with design decisions that were made? Well, I'm not going to show you the whole algorithm. That would be too complicated. I'm going to show you a part of the algorithm. There's actually a paper called Mind Your Outcomes which explains more of the algorithm, but I just want to show you the kind of thinking you do. Okay? Here, each of these boxes is an algorithm. So the initial design is very naive. It's one hop. I will send a message to each one separately. Okay? Maybe I want to do multiple hops. Instead of one hop, I will send doing multiple hops. Maybe I want to do more sophisticated. I do a header body split. Note this is a secure algorithm using cryptographic security, so the header can be like a digital signature. So we split the header and the body, and you can send first headers. Okay. Also, the network can change. A node that leaves, that is no longer a neighbor, might rejoin. Okay. And then which neighbor do you select? Each node has several neighbors, and you can pick one of them. So those are all aspects of the design. And each of these arrows is a design decision. I do multiple hops, I split the header and the body, I figure out how to rejoin the network, I figure out how to do neighbor selection, and each time I do the design, I measure, I compute delta Q, so I have an outcome diagram. For each of these boxes there's a big outcome diagram, and if it's not good enough, I go back and I change the decision. So I have this thing where I'm trying to go forward, and if it's not good, then I undo the decision and I make another decision. So you have this design process, okay? And there's two steps. The first one is preparing. So we have a very initial, very naive design, and we measure the delta Q. So I'm going to show you how that works. And the second step is making design decisions. So this is actually a very interesting process. Normally people don't really explain how they design an algorithm, okay? Here, each design decision will define a new outcome diagram and a new delta Q, and each step we decide whether that's good or whether to go back. So you're going forward and backward and computing delta Qs all the time, okay? So that's kind of the idea, but I'll show you in a minute how it works. The first step is measuring the delta Q. Okay? Measure delta Q between two nodes across the network. How do you do that? Well, that's actually an engineering thing. It requires some work. There's some basic information. What are the block sizes? So we'll assume from 64 kilobytes to 2 megabytes in 5 sizes. The network speed, well, we will measure TCP speeds. The geographical distance, we actually keep it simple. We assume short, which is the same data center, medium, which is the same continent, and long, which is different continents. So this is a worldwide, of course, algorithm. Huh? And network congestion, here we're in the initial stage we ignore network congestion. Okay? And we'll start with single hop delta Qs. And then we go to multiple hops. So a multiple hop can be faster. Right? It's a multiple hop delta Q is computed from a single hop by doing sequential composition. Okay? And once we have multiple hop between two nodes, we have to weight it because actually we need a random path. So we have to do like a sum of paths, so weighted sum. So we're using probabilistic choice for that. Okay, so let me make some real diagrams. Okay, here we have one hop. Now we have short, medium, and long, which I showed you. Short hops, medium hops, and long hops. And we combine them using probabilistic choice. So this gives you this kind of step function. Each of the colors is a size. So 64 kilobyte is here, okay? Short, medium, long. And once you do that, you get 100%. The red one is 256, and the purple one here is 2 megabytes, okay? This is a measured delay, cumulative probability with a measured delay, okay? For short, medium, and long. Now we do multiple hops using convolution. So we combine these. What happens if the algorithm does multiple hops? So here on the left, we get a 64 kilobyte. So we're combining the 64 kilobyte, and we're actually convolving it with itself, multiple hops, 1 hop, 2, 3, 4, 5. You can see 5 hops, it's a little bit more continuous. Here is the 1 megabyte also. So you can see how it's working. So the transfer delay for 5 hops will be, the 50% point is going to be a little bit more than 1 second. Okay. Here the 50% point is going to be less than that. Okay. Multi-hop is computed. So we measure that, we compute the multi-hop, and then the final point is we do random paths. And this is computed in a random graph of 2,500 nodes of degree 10. How many paths of each length? So we do a weighted sum of the 1, 2, 3, 4, and 5 hop paths. And this gives us the final delta Q. So here, the blue one is the 64 kilobyte delta Q. And then here we have the 256 and so on. Okay? So this will give us the measured and computed delta Q for the delay transfer between two random nodes. Okay? So that's the first step, the delta Q. The second step is now designing. And this is a little bit, I'll try to explain it in a nice way. The outcome diagram is quite complicated. I'm only going to show you a piece of it. Here is a part of the outcome diagram. This outcome diagram is for obtaining 3 blocks from the fastest neighbor. 1, 2, 3. And each block is divided into header and body. And you need to get permission before transmission. So you send a header, you ask for permission. If you get the permission, you can transmit the body. Okay? So how is this determined? Here you have, so you have the 2 operators here. So the all to finish and the first to finish, and I'll explain what it means. You have what it means. You have the 3 steps here. Okay? And each of these outcomes has its delta Q, and using the formulas, the semantics, you can compute the delta Q of the whole thing. Now let me explain one of the steps. So first thing, let me refresh your memory of the 2 operators. So we have all to finish. So we have a number of possibilities here that we're doing in parallel. For example, if we want to obtain 1 block from each neighbor, so we have 5 neighbors and we want 1 block from each of the neighbors, we have to wait for all of them. So that's an all to finish operator. Okay? Now, this one is a first to finish. We're only waiting for 1 outcome. Let's say we have a bunch of neighbors and we just want to find out which is the fastest one. That is a first to finish operator. Okay? Not an all to finish, just a first to finish. So, if we do that, we have the following thing. Okay? Here, these 3 red rectangles here are obtaining 1 block from a fastest neighbor. 1, another, and another one. And then they are connected using all to finish because we want to obtain 3 blocks in order. First one, well, we want to obtain 3 ordered blocks, but we're asking for them in parallel. 1, 2, 3. And for each one, we're asking permission. So we're asking permission and we get authorization back. So we ask permission, authorization, permission, authorization, permission, authorization. And we combine all that together and we can compute the delta Q for this. And we can change our design. Here we're doing 3 blocks. Maybe we want 2. Maybe it depends on how many we're asking for the fastest and so on. So we can change our design and figure out the delta Q. Okay? Okay? So the resulting outcome diagram, let's say it's this one, models the causality and performance of this transfer according to the algorithm, and we can compute the delta Q. Okay? Of course, you don't want to do it by hand. For Cardano-Shelley, PSOL, this was work, so they are actually subcontracted by IOG. They are working for IOG, even today, now. So they are continually involved with the development of this system. And this took several years, okay? So they designed this algorithm, discussing with the engineers of IOG. And the design decisions they take, we kind of summarize them. So this is some of the design decisions that they did, okay? And so you would not normally want to do this by hand. You would do this with a software tool, okay? So one of the goals of the project that we're still working on is building software tools, because you don't want to manipulate such diagrams by hand. What a tool would do that very easily, yeah? So you can see, you can actually explore different design decisions and compute the performance before building the system. Okay? Okay, so let me go on now. Let me go to the final part of the introduction to ΔQSD. So far up to now, we have systems with no dependencies, where each piece works independently. They're all separate and independent. Okay, that's not always how the real world works, okay? So we have seen the first part, design the system with independent parts. Pieces of software, humans, all independent. But in real world, systems sometimes have dependencies. Realistic systems, you have to add dependencies. So most of the system is independent, you have to add dependencies. And so now I'm going to show you how to go to the next level and how to add dependencies. And that can show you exactly where overload, for example, is going to happen. And I'm going to show you some examples, shared resources, like congestion, for example, or iterative queries, where humans interact with the system. And then in general, the concept of slack and hazard. How close to the edge are you? Okay. So here, let me say something about shared resources. Okay. So real systems have shared resources. So for example, the pieces of software running on the same CPU, or many different streams of data are going across the same network connection. Okay. And so we have to model that. If we want a correct prediction, we have to model the sharing. And there's two resources that I want to especially talk about. There are different kinds of resources. So one important kind of resource is an ephemeral resource. There's also something called a threshold resource. And then there's other resources, accumulative resources, which I won't talk about. An ephemeral resource is a resource which is available right now. And if you don't use it now, it's lost. CPU power, okay? The CPU can do so many gigahertz, so many megaflops right now, and it's a resource. If you don't use that now, then it's not used, okay? So it's ephemeral, which means it's transient. If you don't use it at a particular instant, it's lost. Maybe, again, it's available later, but that particular resource is lost if you don't use it, okay? Another one is a threshold resource, where something goes up to a certain level, and if you use more, it has an enormous effect on delta Q. So, for example, thrashing. Do you know what thrashing is? No. Oh, thrashing is what happens in a memory, a process, and is running on an operating system. Each process that you run, the process has a certain size of memory that it's allocating from the operating system. No? 256 megabytes, for example. But it doesn't need all of that. It has something called a working set, which is the size of the memory it actually needs, maybe 75 megabytes. And if you allocate that amount of RAM, it will run fine. But if you don't have that amount of RAM, it will have to do swapping. You know, virtual memory has to do swapping on disk. So it will still run, but it will be much slower. So if the amount of available RAM is less than the working set size, the system will thrash. That means the performance will go way, way down. Okay? Now, this is less of a problem, maybe, but maybe you have seen it if you've run lots of very big programs. Okay? This is a threshold resource. As long as the amount of available RAM is greater than the working set size, you're fine. Once you go past the threshold, you're dead. Congestion is also an example of a threshold resource. If I have two streams of packets going into a single memory and going to a queue component, if the total load gets bigger than 0.8, the delay will go enormously up. We saw it before the break. That's a threshold. As long as the load is less than that, you're fine. Okay, so that's a threshold resource. And there are other resources like battery power or thermal management, but resources with time constant or with cumulative, which I will not talk about. I'll just talk about threshold and ephemeral. Here's an example of how to model congestion using ΔQSD. We have a router. So this router is an MM1K queue, as we said. So basically it has a buffer and it has a server that figures out where to go. And there's two streams of messages coming in. And each of these two streams has a load, AX and AY. And the total offered load is A, which is AX plus AY. The two streams are sharing the same router. And the delta Q of that router is going to be a function of the offered load. And as we saw before, if the offered load gets bigger than 0.8, boom, it just goes way bad, okay? So that is exactly congestion. This is modeling exactly congestion. Buffer overload, message overflow, message drop. When the total offered load gets greater than 0.8, then you start having congestion. Now, in our model, to compute that, you have a set of equations. Okay? The delta Q here is a function of these two parameters. So it's just adding an extra equation between these two things. Okay? So this is very easy to model using ΔQSD. Of course, solving the equation might be harder, but I'll give you an example of that in a few minutes. See, so this is how to model congestion. Here's another interesting one. This is a example of threshold resource, CPU power. Let's say we have these two pieces of software, and they're running on the same processor core. So they're sharing CPU power, okay? Each one uses a fraction of the CPU. And of course, the sum of these, well, actually it has to be less than or equal to 1. Let's say it's equal to 1. Okay, so that's a constraint. Now, if this one needs more CPU power, then there's less CPU power available here. But if both of them need a lot, they won't get it, and the system will slow down. So this gives me an extra constraint, an extra equation in my computation of delta Q. You see that? And with this I can figure out, and I can even push the system to the edge. Okay? I can push it to the edge and see when it's going to break down. I can increase the input load. Okay? These guys will be, the more things coming in, the higher will be the CPU usage, and they will try to get more, or else the delta Q will increase. And you solve that equation, you can see exactly when the thing is going to break down. Okay? So that's the second example. Let me show now you a very interesting example of the human-machine interaction. Iterative query. It's basically a cyclic thing. So here's an iterative process. So I am sitting in front of my computer, and I see something on my website, and I click. It does something. I see a new website. I click again. So this is iterative, huh? This is called browsing the web, okay, or whatever, huh? Something that happens all the time. Well, we can compute it. So this models many human-computer interactions. It also models software doing iterative queries to a database. So software requests something from database, gets an answer, does a computation, makes another request, and so on, and does computation like that, okay? Now we can actually compute the delta Q for this iterative system. It's very interesting, actually, and I will do it with you. How do we do it? How do we compute the performance of this thing? Because the delta Qs are going to depend on the load and so on, and the load will depend on delta Qs. You have this recursive dependency. Okay, so first of all, you have to write an outcome diagram. There's two kinds of outcomes here. Let me say the server outcome and the user outcome. So the server outcome is very easy. The query comes in, it does something, and the result comes out. So the server outcome is a pair with query as the start and result as the end. That's server outcome. But the user outcome is more interesting. So the user sees the server result, thinks a little bit, and makes another query. So let me write it like this. The user sees a result here, thinks, and makes another query, okay, which I will write as Qn plus 1. And that makes a cycle, because this Qn plus 1 will give me another server outcome. So you have this causal sequence of outcomes, which goes on forever in this model. Huh? So it starts with a single, say a single server outcome, a thing coming here, and then a user doing something, then a server, user, and so on. Server, user, server, user, server, user. And now let's compute the delta Q for this thing. Okay? Okay, make a model of this. Okay, how does it work? There's actually two equations. There's the load of the server, which is the rate of messages coming in. The server, delta Q, is a function of the load A, as we saw before. Huh? Okay? And the load is also going to depend on the user, the thinking time of the user. Okay? So it's the total delay, actually this should be a convolution, but the total delay of these two, okay, which is, well actually I'm adding it because this is just going to be a constant, okay? It's actually a slightly simplified, should be convolution, but the convolution is going to be just an addition because I'm going to assume that the thinking time is simple, okay? So we can compute the load. This is a recursive equation. The load here is the expected rate of queries. What is the expected rate of queries? We take the probability density function here of the time per unit of time. So this is the load per unit of time, and we integrate that. So we have this funny equation, and we can solve it. Let me solve it for you. Okay, so we'll assume that the server is running at low load, okay? It's in a good case. The load is less than 1. So from our previous diagram, it's this. This is the approximation. AS over 1 minus A. We have the server time S. We assume the user has some thinking time, D, which I call D here, which we will vary, but I'll show it's a parameter here. Combining those two, so this is the overall time of the whole thing. So this is the thinking time plus this server delay plus the server density here. If I make the derivative of this, I get the probability density function, okay, of the delay of one iteration, okay, and the load is going to be this divided by the time. Huh? Now, you can work out the integral. I leave that as an exercise. So I spent an afternoon working it out, and it gives you this very interesting function. It's a recursive function. A, the load, is equal to 1 over S times the natural log of 1 plus 1 over D over S plus A divided by 1 minus A. So I've made the approximation of uniform distribution here. Huh? Notice there's a very interesting thing, parameter here, D over S. It's the ratio between the user thinking time and the server thinking time. So that's actually very interesting. Is the user taking a long time to think or not? Okay, so then we can make a solution. So the way to make this, I will solve it graphically. So I will draw this graph of this function, and I will intersect with a line where it's just A, okay, the 45 degrees. That gives me this. So this is the input A. The curve here is this natural log, and this 45-degree line is the result is exactly A. So the solutions will be these intersections, huh? And I made a couple of possibilities depending on how fast the user thinks. Okay? If the user thinks as fast as the server, then the load will be 0.44 here. Okay? If the user thinks very fast, it will be faster. But if the user is a slow guy, is taking 5 times the server to think, the overall performance will be lower, of course. Huh? So with this, we have now computed the load of this recursive system. It's interesting, huh? So you can actually really figure out how systems are going to behave. This is still an approximation. Huh? I'm using the uniform distribution here, but it's an interesting result. Huh? You can actually, you can solve it graphically. Yeah? I take 0.4 something, then I basically, but it converges very fast. Huh? So there's no problem. But I don't need to make a more exact solution. Okay. So measuring load, so that's an interesting point. We're measuring load here. Okay, number of events per second, that's the load, but also what is the time between events? So the right way to talk about load is work per unit of time. So it's the number of events per second. So this means you can just add up. Loads can be added up. Huh? Let me show you another example. This is where you have two servers connected, one to the other. Two pieces of software, basically. One is querying, and then the other one is responding, querying, circling like that. It could also be humans. Two collaborating human teams that are communicating with one another. Now, if this S1 and S2 are different, almost all it's the slow server that drives everything, okay? All the waiting messages will queue up at the slow server. You can show that with this example. So if you have two human teams, the slowest team is the one going to be driving everything. It doesn't help to make the faster team better, okay? Okay, so that's just some examples of shared resources. Let me now finish by doing more general. We want a system that really works under high load. Telephone system, there's a natural catastrophe. Everybody wants to make a phone call. What happens? Well, if you're not careful, the whole telephone system will collapse, okay? But we don't want that. Okay, so let's think about that. The system is stressed. High load. Is it able to handle that? Does it have some reservability? So the first concept is to see how close to the edge are we running? And that introduces slack and hazard concepts. Slack means the system is far away. It has some reserve power, but hazard means it has no reserve power. It's in a dangerous situation. And we can compute that by comparing two delta Qs. The required delta Q, the one that you need, and the one that the system is actually delivering, of course. And if one of them they're intersecting, you have a problem. Huh? And then I'll say a little bit about hierarchy of hazards. There can be more and more serious ones. So here's the basic idea. So the blue, this thin blue line here, is the required delta Q. And the black one is what the system is delivering. Okay? Now Q2, delta Q2 is not, here it's not delivering. Okay? There's some probability here that it will be in the red part. That means the actual delay will be higher than what it's supposed to be giving. Okay? So that's a hazard. Whereas the delta Q1 is good. It's far away from the blue one, and it's actually some distance away, and this is called, the green part is called the slack, okay? So it has a little bit of reserve power, and if you want to compute that, here's kind of the way to compute it. The blue one here is what I want, the required, and the black one is what the system is actually giving me, okay? Now notice there's a part here where it's kind of a problem, because the system is giving me a higher delay than what I need, which is not good, okay? So this is risk. So there's some terminology. A hazard is the probability. So the probability is P1 minus P0. It's the probability that you're in this area, which is actually pretty high in this case. And the impact is the cost when the problem does occur. So if I'm here, the impact is this. This is the cost. I have some extra delay. So the risk is actually, the total risk is the weighted impact. Okay, it's kind of the expected impact. So it's in some sense the area of this orange part. Okay, so for each probability here, I have some impact. So I kind of take the average. So it's the integral of IDP. So the risk is kind of the weighted, the expected delay. It's the expected impact problem that I'm getting. Okay? So this is how to compute it. And now let me give you a kind of hierarchy of the hazards, and then I finish with how to solve it. Okay? So this is only scratching the surface, huh? So so you have 5 orders of hazards. The first 2 are actually very nice. The first 2 is your system is actually compositional. There's no dependencies yet. The first one is to say your system is causal. It's just following causality. So that's fine. That's very easy. Yeah? The second one is all the components are independent. Will deliver delta Q within the requirements when all the components are independent. So that's still very nice. And now if we go higher, things get worse. So the second, order 2, is the system still works, but you have to schedule things. So maybe I have 2 tasks, and I have to make sure that they're done in a certain order, or I have several tasks. I have to schedule them. So the QTA, so the delta Qs, required delta Qs, can be maintained, but I have to do some work. I have to schedule things. And then the final 2 are when that's not enough. These are called correlation, internal correlation, external correlation. This is really the worst cases. Internal correlation is when the system is kind of shooting itself in the foot. For example, maybe all devices on your system will do some kind of a maintenance at midnight, which is maybe stupid because at midnight the system will overload itself. Okay, so you don't want to use the system at midnight. That can happen. So maybe you want to worry about that. But the final one is external correlation. Is the system sensitive to extreme behavior of the users? When there's a natural catastrophe, all users will maybe want to make a phone call. Okay. So this one, the fourth one, is the one that's the hardest to design for. Okay. And let me just give a few ideas on it, because this is just an introduction, but we're still working out exactly how to present the higher order hazards. But there's some principles, okay? So first of all, you need to treat the hazard 3 and 4. And so ideally, you don't want to get there. You don't want the load to be greater than 0.8. But that is not going to happen. It will get bigger. Okay? And you cannot over-dimension the system. So the load will get higher, so you need to do other techniques. Okay? So you must deal with the overload. You cannot avoid it. And at all time scales, so there's a notion of time scale. When the overload is very short, you can handle it at a longer time scale, and each time scale has its own technique. Okay? And now let me just give a summary of how to do it. You have to build the system in the following way. You have a base system. The base system, which is not just doing the regular stuff, but it has to obey 2 rules. The first rule, the system may behave badly, but it must never break. That means if you overload the system, maybe it doesn't work, but it shouldn't break. That means if the load goes away, it should start working again. Okay? So an overloaded system must never break. This is actually very similar to eventually perfect algorithms. while the failure detector is making mistakes, the algorithm should not give a bad result. And when the mistakes go away, it can give a good result. Okay? So it's kind of similar. The system may behave badly, but it must never break. So that's the first rule. So when you build a system, you have to satisfy that rule. And the second rule is, when it's overloaded, there must be some guaranteed minimum performance. The performance cannot go down to 0. There must be some number greater than 0 that the performance goes to. For example, if I keep overloading my database, there must be some queries that succeed. So, for example, I can define high priority packets in a network, and they will always pass, no matter what the load is, because the number of these will be very small, and even if the rest of the system is totally overloaded, I have designed the system so that the high priority packets will always pass. There must be some guaranteed minimum performance that's greater than 0. Okay? If you obey these two rules, then you could have a system that lives in high load. Okay? In the phone example of a national phone network, there must be some phone calls that always go through. For example, certain kinds of emergency calls must always go through, even if no other calls get through. And this will allow the system to basically, the higher levels to work at some level. Okay? So that's the base system. And on top of that, you can design levels of management levels. And there's several levels of management. The first level is to drop non-essential traffic. So you basically kick out things that are non-essential. The second level is you reconfigure, but this cannot be done very fast. So this is at a longer delay. You reconfigure, you put a human in the loop, so the human makes decisions. And the final level is up to years. Well, you redesign the system. Okay, so this is the long-term solution. Okay, if you have a nuclear accident, then there was something wrong in the design of your reactor. Okay, if you have a supervolcano eruption, well, maybe you don't want to live near supervolcanoes. You have to do a long-term thing. In fact, these events, humans don't realize how bad they are. There is something called Carrington event. Does anybody know what a Carrington event is? And no one ever, in the newspapers almost never talk about this. Strange, huh? Well, I think it was in 1860 something, in September, you can look it up, there was an eruption from the sun which hit the earth and which caused a complete disruption of the electrical system. Of course, there was no internet in those days, but there were telegraph operators. The telegraph operators saw sparks coming out of their stations. That's pretty amazing, isn't it? Sparks. Sparks coming out. It's estimated, and there was no internet in those days, telegraph. It's estimated that if the Carrington event happens today, it will cause 1 trillion euros of damage to the internet. And these events are estimated to happen every couple of centuries. And a few years ago, there was an enormous ejection from the sun which missed the earth. Maybe next time it will hit the earth, right? So this kind of disaster, we hope that the governments are thinking about them, okay? There's a Carrington event, which will destroy the internet. There's another kind of event, which I didn't write here, called the Miyake event, which is rarer. It's like once every 1,000 years. If that one occurs, it would basically destroy all the electrical infrastructure of the part of the Earth that is facing the sun. Okay, maybe not in the night part, but half of the Earth. This is not just the internet, which is very fragile. It will destroy all the electrical distribution networks, all the transformers. It will all be destroyed. It's amazing, isn't it? And one of these has happened, and it was in the year 800 something. This is a Miyake event. You can look it up. This is all known stuff. I'm not inventing this, okay? And of course, supervolcanoes, they are rarer. So I would not live in Yellowstone Park, because that's on top of a supervolcano. And it is estimated that once every 50,000 years, one of these guys will erupt, and it will cause 1,000 cubic kilometers of ejecta to cover the Earth. That's basically covering all of North America to this level of depth. All of North America, something like that. Huh? It's a lot, okay? There was a small one, which you may have heard of, in 1880 something, called the Krakatoa eruption. Have you heard of that one? This one was very small. It was in Java somewhere in the island. It caused only like 50,000 deaths. Maybe I'm quoting from memory. Yeah? It was so loud that everyone living within 100 kilometers of it had their eardrums punctured and became deaf. 100 kilometers, okay? That's how loud it was, 150 decibels at 100 kilometers. And it's not even a very big one. It was only, what, 20 cubic kilometers of ejecta, something that's very small compared to supervolcano. Okay, so if you really want to build systems that survive, it's not so easy, okay? So this is kind of the extreme case, but these cases are very important. Now, notice that most systems today do not satisfy that. Most of the internet today will not survive if we have a Carrington event, okay? And what do you think of that? And on that very pleasant note, I will end the course for today. Thank you.